In this lecture, we shall be considering the topic of data transformation. Recall what we discussed regarding linear regression. Certain assumptions underpin linear regression, one of which, or some of these assumptions, include the presence of a linear relationship, ensuring homoscedasticity, and also that residuals should be normally distributed. So the question to ask is, what if these assumptions are not met? Is there anything that we can do? Certainly, there are some approaches, and one of these is to consider the strategy of data transformation. And so in this lecture, we shall be looking at some common data transformations and methods to achieve that, which include log, square root, square, arcsin-root. We'll also introduce the concept of the ladder of powers and Box-Cox methods that help to select an optimal normalizing transformation. Because the goal of the data transformation is to try to help meet the assumptions so that we can carry out our regression. However, it comes with certain trade-offs. So for example, log transformation will give us a multiplicative geometric mean model, and in this case the coefficients will represent percentage change in original outcome after exponentiation. So transformations may improve model validity but complicate interpretation, and they may not always resolve the underlying data issues. So why do we carry out data transformations? The first reason is to linearize the regression model. The second reason is to stabilize variance. So we want to reduce the heterogeneity of variances, otherwise known as heteroscedasticity, which contrasts with homoscedasticity. We also would carry out data transformation to normalize variables. Some transformations will often serve more than one purpose. So, a transformation that linearizes a variable can also normalize it. We would want to carry out data transformation for theoretical reasons. It's also possible that the dependent variable has a probability distribution in which the mean is related to the variance. Sometimes, after we have examined the residuals, we may find empirical evidence which provides us reason for us to carry out a data transformation. We also need to understand that not all relationships between variables are necessarily linear. And sometimes when we examine the data, we see such relationships and we want to convert them into a linear form. And so that brings us back to the theoretical considerations. What kind of variables can be transformed? We can transform the dependent variable. We can transform individual predictor variables. We can transform both dependent and independent variables. When we transform the dependent variable, we need to understand that this will affect the relationship of the dependent variable with all of the predictor variables in the model. So that's a significant impact of transforming the dependent variable. There are major drawbacks to data transformation. So interpretation of the regression model, once we've carried out the data transformation, can be difficult. And so we need to bear in mind that the interpretation has to do with the transformed variables and not the original variables themselves. The relationship between the transformed variable and the original variable may be very difficult to understand or even confusing. And then transformation may not even be able to rectify the problems in the original data. And so the regression analysis would still be suspect, giving us biased or erroneous results or estimates. There are several algorithms that we can use to transform data. One of the commonest and most common ones that is used is the log transformation, and this basically just applies the logarithm of the natural logarithm to the dependent variable, and this is for y greater than 0, so we use it for non-negative values. Another algorithm that may be used is the square root transformation. So we take the square root of the dependent variable. Again, this is applicable for non-negative values of y. We have the square transformation. We also have the arcsin-root transformation, and then Poisson distribution. So in Poisson distribution, we do this when the distribution of the variable is a Poisson distribution. We also have the binomial distribution, and if you look at this slide, you can see that the binomial distribution is similar to the arcsin-root transformation, so they are similar. And if you also look at this, you discover that the Poisson distribution is similar. The data transformation for the Poisson distribution is similar to that for the square root transformation, so which tells us that some of these things have commonalities and overlapping boundaries. And then negative binomial distribution. Don't expect you to memorize this, but it's just to be aware of the existence of this approach, and as we go on in this lecture, we will see an applied example of data being transformed. And the truth is, there are certain circumstances where you probably would need to do some data transformation. So we'll look at the log transformation, and the purpose of that is to linearize the regression model, especially if we see that the relationship is curvilinear upward. So if we plotted the untransformed y against x, so to speak, we find that it has an exponential gradient, so it's curvilinear upward, so it's curving upward, curving upward. And so the reason we do this log transformation is to stabilize the variance, because if the data is not transformed, we find that the variance of the residuals increases markedly with increasing y, whereas one of the assumptions of the linear regression model is that of what we call homoscedasticity, so the variance does not change. We also use it to normalize y when the distribution of the residuals is positively skewed. So again, so this is the purpose of log transformation. And then for the square root transformation, that is used to stabilize variance when proportional to the mean of y, especially when y approximates a Poisson distribution, and so we already saw that earlier. If the variance is proportional to the mean, and this is one of the peculiarities of the Poisson distribution, the variance is proportional to the mean. In square transformation, we use that to linearize x when it's curvilinear downward, so the slope decreases as x increases. So this is kind of like the reverse form of when we use the log transformation. Remember, in the log transformation, we apply that when the relationship between x and y is curvilinear upward. And so in contrast, if it's the other way around, then you may want to think about applying the square transformation. The arcsin transformation is used when y is a proportional rate. So we're looking at rates. Remember, rates has to do with time, so we can use the arcsin-root transformation for rates or proportions. So what to do if you can't figure out which transformation to use? So in this graphic here, we see a right skewed distribution, which is now transformed and becomes normally distributed. So for example, if you look at this first graph, you see, so this is where the mean lies, so there's a right skew, and then following data transformation, it's a bit more normal, and you find the mean is central and the curve is symmetric. So there are two approaches. We can use what is called the ladder of powers, or we can use the Box-Cox transformation. The ladder of powers just basically applies this sequence of transformations and test for normality. And so might take the cube, take the square, and then this is the unchanged or untransformed data, and then take the square root, and then take the natural logarithm, and then consider the this as well, and so on and so forth. And so it does this in sequence and then tests for normality. Of course, one could do this manually. I mean, it's a trivial task to test this in your software that you're using to analyze. But for example, in Stata, there's a simple command that gives this. So using the Stata statistical software, if you just type ladder y into your terminal, it runs this automatically and gives you an output. So again, not expecting that you would do this manually by yourself, but it's just to be aware of the options that are available to you. The second approach is to use the Box-Cox transformation, and in this case you find the value for the transformation shown here. So the values being transformed must strictly be positive, that is greater than 0. And so what is found is the value u, which put into this formula normalizes the transform variable. And so again, in Stata, the command to do that is given as shown. So it's just for us to be aware. So this is the Box-Cox transformation. So y raised to power u minus 1 divided by u, and so solving for the value of u, which normalizes the transform variable. So let's look at an example, a practical example that illustrates this approach. So suppose we have a regression model that seeks to predict the number of oocytes produced following an IVF cycle. So this is real life data obtained from real people. So looking at the histogram, it's apparent that the number of oocytes is right skewed. It's not normally distributed. So if you look at this histogram, we can see how it goes. So a lot of oocytes here at the lower end, and then very few as we move towards the right. So it's most definitely right skewed. And so this extract here is from the statistical analysis report which was done, and it comments on this histogram. It says, look, this is a deviation from one of the assumptions of linear regression models, which requires the dependent variable to be normally distributed. Since the outcome variable is not normally distributed, what do we then do? There are a number of approaches. We can try the following: linear regression modeling with log transformed outcome. So we've already talked about log transformation. Or generalized linear modeling with a gamma distribution, since the outcome variable is a right skewed non-negative distribution. So for this statistical analysis, both linear regression models with log transformed dependent variable and generalized linear modeling with a gamma distribution were examined. However, only the linear regression models are reported, as they provided the better fit to the data. So this was work that I actually did some time back, working on a project. So this was a statistical analysis which I did carry out. So like I said, this is a real life example. So the log transformation of the outcome variable. So how does that work out? So we can log transform the outcome variable. In this case, we are talking about number of oocytes produced during an IVF cycle. So this means that we are looking at a multiplicative geometric mean model. So that's what log transformation does. So in refreshing our memory, this is the arithmetic mean. I mean, we know what it is. You add up all your observations, the value of y, for your observations, and then divide by the number of observations. So pretty straightforward. And so that's what this formula represents. So sum of all y from 1 to n divided by n. In contrast to the arithmetic mean, the geometric mean is multiplicative. So this symbol here just means multiply. So we're taking the product of all y and then taking the nth root of it. So the nth root of the product of all of y. And this is equivalent to the natural logarithm raised to 1 over n and then sum of the log of y. So this is really what this is. So it's a geometric mean, and this is how we get it. So if we look at the linear regression with the log transformed outcome, like I've already stated, it's a multiplicative geometric mean model. And so if you take the log of y here, this is the expected variable, the predicted variable or value. Then the right side of the regression equation is similar to what we know. So the beta naught plus beta 1 x1 all the way to the nth variable. And so if you take the exponent of both sides, because this is log y on this side, so if you want to take the actual y, you take the exponent of it, and so of course you have to do that on both sides, and so this becomes this. And of course from maths we know that this is equivalent to this. And so this is interpretable only in terms of change in geometric mean. So it assumes multiplicative effects on the original outcome by the predictor. So because it's a geometric mean, we're not dealing with additive effects now, we're dealing with multiplicative effects. So so each unit change is going to result in a multiplicative effect. So what does that mean? We'll see that in action here. So and this is the regression output for the log transformed outcome. So remember that in this case now the dependent variable has been log transformed, and so you look at that, and these are the variables we put in. So we had endometriosis, short protocol, which is a treatment protocol, and then use of cetrotide and Zoladex, and so we have an R squared of 0.244. I hope we do remember what R squared means. So from the table we see that the model can be written as the natural log of the number of oocytes equals to beta naught plus beta 1 endometriosis plus beta 2 short protocol, beta 3 cetrotide plus beta 4 Zoladex. So all we need to do is plug in all these values into their corresponding variables. So beta naught is the intercept, so that's 2.369, which we have here, and then 0.234 endometriosis, short protocol, and all that. So these variables just are represented by either 1 or 0. So if there's endometriosis, this is a 1. If there's no endometriosis, this is a 0. So 0 times this, so it cancels out. So essentially this is how the equation works. So with that, once you calculate that out, all you need to do is exponentiate the coefficient and then subtract 1 from this number. So and then multiply by 100 to give the percent increase or decrease. So in this case we're not talking about additive but multiplicative effect. So in the dependent variable, for every 1 unit increase in the independent variable. So for treatment protocol, for example, recall that treatment protocol here is given by the coefficient 0.672, and so treatment protocol, the short protocol, is either used, represented by 1, or not used at all, represented by 0. So if you plug that in here, so we have e to the power minus 0.672 minus 1 times 100, and this gives us minus 48.9. So what does that mean? It just means that, so the negative tells us is a decrease, so it means that there's a 48.9% decrease in the number of oocytes compared to the other protocol, which is the long protocol. So and so this is how you interpret a log transformed outcome when you've done a linear regression for it. So this is a worked example, and helps to illustrate how we do data transformations.